Okay, let's get started. So before we get into some content, just a reminder, we had a few questions on Piazza. If you are feeling sick at all, don't come to class, don't come to campus. Just stay home. If you're ever feeling, even if it's, whether it's COVID or not, if you're feeling sick, just stay home. We'll take care of everything. You're not going to be punished for that. Even if it's a lab, the whole schedule of this course, having the 2 chances to do each quiz and interview specifically, it's all designed so you can miss a day or even a week and still recover and still come back. So if you're feeling sick, just stay home, get better, rest. Worry about 116 when you feel better. Don't come in and get everyone else sick is the worst thing. If we're doing all this stuff for the pandemic, the one thing that can come of it, which was nice last year too, is that we don't have that, you got that bug that's been going around. We shouldn't have that anymore if we're all wearing masks and doing all this stuff. That's something we can get out of all this. Last semester was nice, not getting sick. Every fall, everybody would get sick on campus. We shouldn't have that this semester. If you're feeling sick, just stay home. What's up, Dragos? All right, so let's get into some content. Anybody have questions that we need to be addressed before we get started? Dragos is the only one who said hi. I guess I can say hi to the TAs. Hi, TAs. All right, I didn't miss anyone. Ren and Rislana, hi. Oh, I see, because someone's got to do it, and then the next line. I was reading that as one sentence that just said, somebody's got to do it. Hello, I don't know. My brain wasn't working. Hi, Cole. All right, so let's get into this. So I did misspeak last lecture. I forgot that I switched around the order of lectures a little bit. And I thought that I still had merge sort today. Merge sort is actually Friday because I want to get this lecture in the schedule earlier because this is very applicable to your homework. It really helps out with your homework. This lecture is just kind of a potpourri of topics of applications of functional programming that you may find very useful for your homework throughout all of the objectives, all the tasks, all 6 lecture tasks and the 2 application objectives. We're just going to see a whole bunch of applications of using functions. So after this one, you're going to definitely be able to do lecture task 1. For this, writing 2 methods, average and top K. Average is going to take, and writing these both completely generically. So average is going to take a list of elements, a list of things, and a function that's going to turn those things into doubles. Take in an object of this type parameter, and then return a double. What we want is the average of all those doubles after calling the function on each element of the data structure. So this is kind of a parallel to a 115 question. If we, in 115, said, here's a list of ints, return the average. That would be a good 115 style question. Now we want to do the same thing, but completely generically, taking a type parameter and taking a function that's going to determine what we're going to take the average of that type parameter. So maybe the type parameter is players, and we want to take the average of their current HP, for example. I don't know why we'd want to do that, but maybe that's what we want to do. We would take in a list of players, and then the function would take in a player and return player.hp. So we can take the average of anything. This is one average function, one average method to do all of your averaging everything. That's our goal here, writing things completely generically. So we write things once and reuse them whenever we need them. Give them the type parameter, give it the function of whatever we want to average, and then have it take care of it. Same exact structure, top K is going to return the top K elements based on a function that takes in a T and returns a double. So sort based on that function, and then return the top K of those elements. And of course, testing. All right, so let's talk about one more thing. We will talk a little bit about sorting today. It's all about sorting this week. So we saw many things of how you can sort, and I said there's no stop in the way you can sort things. But there's one thing that I didn't go in detail with. I alluded to it and said with that you can do whatever you want. I want to give a specific example of this, of sorting with extra information that's not given to the sorting algorithm, and show you a way we can do that. We could do this with OOP. We could have an object that's doing the sorting with a method that sorts, and then have that method depend on the state variables. It's the way I alluded to on Monday. But we can also get a little fancier here. So I mentioned that functions are just a type in Scala, and we can do anything we want with them. We can use them. We can have variables of those types of type function. We can have parameters of type function. And we can have return values of type function, but I didn't show you an example of return values, just because Monday's lecture, there was enough going on already. So let's see a method that's going to return a function with some information baked into it. So, for example, we want to sort points based on their, in a 2D plane, based on their distance to a reference point. Say that's how we want to sort the points. How do you write that comparator if you don't know what the reference point is at the time that you write the code? We say we want to get the reference point at runtime. So you want to take a reference point and then sort a whole list of points based on the distance to that, but you don't know what the reference point will be, so you can't just hard code like, oh, it's going to be the point -5, 10. You don't know what that's going to be until you're sorting, until you need to sort a data structure. So to do that, we're going to write a method that's going to take the reference point as a parameter and return a comparator. So say we want to sort these physics vectors, we're going to return a comparator, something that takes 2 physics vectors and returns a Boolean, when in reality we would like a comparator that takes 3 physics vectors, the 2 that we're trying to sort and the reference vector. That's what we would like to do. But we have to conform to the structure of a comparator, which is it only takes 2 physics vectors, just the ones that we're comparing, and returns a Boolean. So what we're going to do is write a method that's going to create, that function for us. So we take in the reference point, return a function. So this whole method only has one statement, and that statement is a function, so that's going to be the return value. It's going to create a function that takes 2 physics vectors and compares their distance to the reference point. So we're going to return this function, and now that function can be used as a comparator, and it has the information of that reference point built into the function, or I commonly say baked into the function. So now we have a lot more flexibility in our comparators. We can write methods that create comparators based on extra information. This is how we get this extra information in our comparator. Especially for application objective 1, you'll be doing this quite a bit. There are functions, the cost function and the incubator follow very strict structures, but they need a lot of extra information not built into that structure, so we're going to write methods that return functions with that extra structure built in. That'll make more sense when you get to AO2. That's about as, or AO1. It's about as specific as I can get without getting way too deep into it. And then when we want to use this, say we have our reference point, whatever we want to sort by, this might be coming from a data structure, it might be coming from user input. Wherever it's coming from, I'm just creating it right here. And then when we want to sort, we're going to call our method with the parameter that's going to return the comparator, and then we can sort these points based on that comparator, based on the distance to a reference point. Okay, any questions on this? If you can follow this example 100%, you're doing absolutely great with functional programming. Just taking quite a few moving pieces and putting them all together, moving functions around our code in the most complex way that we'll see in this semester is by returning a function. That's the most complex thing we'll do, returning a function. It's kind of mind-boggling when you first see it. So if this takes a while to sink in, that's perfectly fine. But does anybody have questions about it? You're not doing great. Well, you can, so that's an implication. If you can understand this, you're doing great. If you can't understand it, it doesn't mean you're not doing great. It's not how implications work. You might still be doing great if you can't understand this. It's not an if and only if. All right, we'll let that settle. It'll be a little while before you need to write a method that's returning a function. So we'll let that settle for a week or so. Today we want to talk about a whole bunch of collection methods. So in your homework, I'll get right to the point with this. In your homework, I banned var. This is a way for you to be able to do things with data structures without using variables in your code. And we'll see a way to do this specifically, but think of the accumulator pattern that we jam into your heads in 115. We see that all the time. How the hell are you going to do that if you can't use a variable? The first step was initialize some variable and then iterate over your data structure while modifying that variable for each element that you see. How the hell are you going to do that if I'm telling you can't use var? And that's kind of something you have to do to compute the average. You want to apply the accumulator pattern. How the hell do you do that without a var? So that's one of the questions we want to answer today and show you all kinds of techniques, all kinds of built-in stuff built into Scala to be able to work with data structures using functional programming ideas. So let's dive into it. It's just going to be like one after another, showing you methods that exist in Scala, mostly with lists that you can use to work with your data structures. So first, for each. This is your typical for each loop. Every loop that we write in Scala is iterating over a data structure, and those are read as for each loops. For each element in this data structure, call this function. We usually write this using the typical loop syntax, and we say for each element in this data structure, run the code between these two braces. But with the for each syntax, we're going to do the same thing, except we're going to call this function. Instead of having the braces and putting all our code between the braces for a loop, we're going to put it in a function and then give that function to the for each method. So we have a list of strings here. We're going to say this list, words, dot for each, call the for each method on the print line method in this case. It could be a method or a function. As long as it takes in one element of the data type and returns unit, you can call it in the for each loop. So this is helpful. It can simplify quite a few things, but not that helpful because it's returning unit. For each doesn't return anything, it just calls that on the data structure. It's nice if you have a lot of mutable objects in your data structure, references to objects in your data structure. You can call this for the side effects, but you're only calling it for the side effects. And if we can't use variables, we don't really have the idea of side effects. So we're embracing immutability on this project by banning variables. So this isn't going to be too useful, but I want to show this first because I'm going to use this way of printing to the screen in each one of my examples. So I just want to get that out there so you're not asking me what for each is on the other examples. Print line, by definition, is a method that we call for its side effect. Its side effect is printing to the screen. We don't call this to do any computation for any values or anything. It doesn't change any state. It just has the side effect of displaying things to the user. So we call that method for its side effect. All right, so now that we got that one out of the way, let's look at some ones that'll be more, that you'll probably use in your code more for this project. Filter is going to take a Boolean function that takes in a parameter of the type of the list and returns a Boolean. If that Boolean is true, keep it in the returned list. If it's false, that element will not appear in the returned list. And this method returns a new list containing only the elements for which that Boolean function returned true. So here I'm checking the length. Is the length greater than 3? For 0, that's true. For 1 and 2, that's false. For 3, it's true. So the return data structure is only going to have the elements 0 and 3. And I'm using new syntax here, so I want to talk about the new syntax. This underscore is very different than what we saw on Monday. So I want to talk about this syntax. I'm going to be using it throughout this lecture. It's a shorthand that we can use for functions. It cleans up the code a little bit. It's completely optional if you want to specify the longhand way of doing things every single time. That's perfectly fine. You don't have to use this at all. But if you want to start cutting down your typing a little bit, you can use this shorthand. So the shorthand with the underscore, we're going to use the underscore instead of naming our parameters. And as long as Scala can figure out what we're doing, and by that for this case is if you only use the parameter one time, then you can put an underscore and Scala will be like, oh yeah, that's where you want the parameter. So this is the same thing as creating your parameter list, the big arrow, and then the body of the function based on that parameter name. If we do just underscore and the body of the method, we're replacing this whole part where we're naming the parameter and specifying the type of the parameter. So as long as Scala can infer the type, and you only use that variable once, that parameter once, then you can use this shorthand. If you need to use the parameter more than once, you can't use this shorthand, because Scala won't be able to figure out what you mean. So this whole thing, we replaced with just underscore dot length. So whatever the input parameter is, dot length greater than 3 is the entire function. Oh yeah, for each would be good in your testing too. Well, I guess you could do that with a regular loop anyway. But for each, calling an assert, you're calling that for the side effect of testing the code. You don't want any return value from assert, so you could throw your asserts right in a for each call. Or in a function that you throw into a for each call. Map. Especially for AO1, map is quite helpful. Even for LT1, this one you might find helpful. So map is going to take a function and create a new list based on the outputs of that function. Yes? Yeah. Yeah, so why don't I just say print line filter words? So I can do that. If I did print line filter words, mostly I just want another example of for each is my short answer. But if we do print line for each, or print line filter words, then we're leaving it up to Scala how to print that, and it'll print all the values on one line with the braces and quotes around everything. Filter words.for each is going to call print line on every single element. So I'm going to get each element on a new line. That's the only functional difference. But again, mostly I just did it for another example of for each, just so I can start hitting you with example usage. So if I call map with a function, again, I'm using the underscore shorthand, but this is defining a function that's going to take in a double, which is inferred because it's a list of doubles. It's going to take a double and square it, and return the square of that value. So numbers.map is going to go through each element in this list, call this function on that element, and create a new list with all of the return values of that function. So we're going to take 1.0, plug it into this function, square it, that gives us 1. So 1 is the first element of that list that's returned. Take 2, square it, get 4, 3, square it, 9, 4, square it, 16, 5, square it, 25. So we get a new list with the outputs of that function based on the inputs being all the elements of the original list. We can also change the types with a map, my previous example just took a list of doubles and returned a list of doubles. We can also change the type. So the map method of the list class, not to be confused with the map data structure, the map method takes two type parameters, one for the inputs and one for the outputs of the function that you give it. So if you give this a function, and the types can be inferred, if you give this a function that takes the type of the list, it has to take the types of the list as an input, and returns a different type, we can return a list of that return value. Oh, I lost that sentence. We can create a list of the type of the return value of that function. So here I have strings. This is a list of strings, so this underscore has to be a string. Dot length. Length is going to be an int. So I take my list of strings, and I have a function that takes a string and returns an int. So what I'm going to get is a list of ints as the output. So we can change the type by giving it a function that takes one type and returns another. This can be very useful. Like maybe you have a list of t, and you have a function that takes in t's and returns doubles. Well, you can use map to turn your list of t's into a list of doubles, and take the average of that list of doubles. For example, maybe that's something you want to do. We can also use the yield keyword. This has a bit different syntax, but this effectively does the same thing as the map function. It's mostly a personal preference thing of what you want to use. Sometimes, even like for me, myself, sometimes I like yield and sometimes I like map. I'll have different personal preferences based on the specific application or based on, I don't know, just how I'm feeling that day when I write that code. But yield is going to be a bit of different syntax. It's going to let us use the same loop syntax that we've used before. The same loop syntax that we're used to. We're going to loop over the elements of this data structure, and we're going to call this code for each of those elements, except we're going to jam the yield keyword right in between the start of the loop and that first open brace. We're just going to stuff the keyword yield there. And now, instead of just running the code for each element, what the yield keyword does is tell Scala to collect the last statement, the last expression that's executed for each iteration of the loop, and collect them all into a data structure. So you can think of this as this being a function or a method where the return value of that method, the return values after calling this method for each element of the data structure, are all collected into one data structure and then returned. So with the yield word here, we're going to get a data structure returned that's going to collect the kind of return value of the loop, of each iteration of the loop, put them in a data structure, and then we can assign that data structure to a variable or do whatever kind of data structure stuff we want with it. Come on, highlight. Which, in my case, I'm just printing to the screen. So this code does the same thing as the code from 2 slides ago, where I was mapping just integers or doubles to their squares. It does the same exact thing, but with different syntax. So if you want to keep using the standard loop syntax, this is a way to do it, to be able to get our kind of accumulator pattern. Well, we're not quite there yet. But to be able to transform an entire list into another list with similar, related values, this is how you can do that without having to create an empty list and then append to the list for each element. We're not saying numbers equals numbers append math.pow number squared. We're not doing any of that. Plus, it gets away from that function syntax. If you're not comfortable with that yet, the syntax might be a little more friendlier for you. That's all I want to talk about yield, right? Arrow is not the greatest syntax ever. I like this syntax, personally. I mean, in other languages, that's a colon, or in Python, it's the keyword in. I don't know. Keyword in is probably my favorite. But there ain't nothing wrong with that. You're taking elements from this data structure, and putting them into this variable. It speaks a lot through those two symbols. Moving data from here to here. The arrows always follow the right way. For like a map, this key goes to this value. The arrow's always pointing like in the direction of the logic. I'll defend those arrows all day. I didn't like them at first, but I'll defend them these days. Yeah, in-game. I'm not going to argue with in-game. I like in. I like Python. Python like just reads like English sentences. Python's really nice like that. So one thing about the yield keyword is it will always try to return a data structure of the same type that you're iterating over. So if we're iterating over a list, yield is going to return a list, which is nice. That's a nice feature when we're working with lists. But when we're not working with lists, when we're doing something like this, which again, I guess a lot of these really come up in AO1. With AO1, it's hard to do anything without like half of these at least. When we're iterating over something that's not a list, we're going to get some data structure. Now, we could figure out what that data structure is going to be. Like here, we're iterating over a range. That's what this data structure is going to be. But Scala can't return a range. We can't have a range of doubles in this case. So it's going to give us some data structure. Some data structure that we probably don't want to work with. So what we can do is this is going to return a data structure. This whole thing that I have highlighted is going to resolve to a data structure containing those doubles that we want, these values 1 through 5 squared. It's going to contain all those values. But I don't care what data structure it is. I don't want to work with whatever data structure it's going to give me. So I'm going to put parentheses around it to make sure I have the right thing selected, make sure everything inside the parentheses evaluates before anything outside, and then hit it with a to list. Simple, effective, clean. Just hit it with a to list, and now whatever data structure Scala gave me, whatever the yield keyword gave me, I'm going to convert it to a list. Because I like working with lists. I know how to work with lists. Then I'm going to store it as a list. I have a list of doubles now. I ain't messing around with any other, whatever data structure, and I don't know what functionality that data structure is going to have, etc. Just turn it into a list and work with a list. So there are times you have to do this for the genetic algorithm, like when you want to create, say you want to create 20 random animals, you will have something like this. For something in 1 to 20, yield new animals. Convert that to a list, and then work with your list of animals. All right, reduce. Oh, that almost goes off the page. Reduce. Now we're getting into replacing that accumulator pattern. So the accumulator pattern says, okay, initialize some variable to some initial value that's not going to interfere with your logic. Iterate over your data structure and update that accumulator variable for each element that you look at in that data structure. So for whatever it is. Maybe you're summing up the values, initialize some value to 0, then for each element in the data structure, add that to your running total. Then return the running total. That's what we want to do, but we have to use a variable to do that in the 115 way. So let's see some functional programming approaches that are going to replace that variable and replace the way we did that, and clean up our code quite a bit too. You'll notice throughout these weeks where we're talking about functional programming, your code gets a lot more expressive. You can say so much more with so much little code, which can be a double-edged sword. It can make your code a lot more dense and a lot more going on with fewer lines of code, but that can be a good thing. Instead of doing one thing, I'm accumulating values, and you have to have like 5-6 lines of code to be able to do that. Here with functional programming, you basically just say, I'm accumulating variables. I'm accumulating values here. So let's see how to do that. With the reduce function, the reduce method is going to take a function that takes 2 values of the type that we're accumulating and combines all the values in a list using that function. So here I want to take the the sum of the squares of all the values in this list. That's what I want to do. So I have some function. It's going to take two values of the type of the list and return a value of that type after doing whatever processing I want to do. The first variable is going to be your accumulator variable, which will be initialized to the first value in the list. The second value is going to be the element that you're currently visiting. So like the first iteration of this, accumulator will be 1, B will be 2, and we'll have 1 plus 4 is 5. And then we're going to call this function again with 5 as the accumulator, 3 as B. We're going to square B, add it to the accumulator, return 14. And then we're going to have 14 as the accumulator, 4 as B. Square 4, 16, and then, I lost my numbers. Was it 14? Anyway, it ends up being 55, I promise. But you're going to visit each element where each element is B, and then whatever is returned here is going to be the new accumulator variable for the next iteration. Now notice that my example here will break if 1 is not the first value, because 1 never actually got squared. Luckily, 1 squared is just 1. So we can get away with it for this example. But that's something you need to be aware of if you're using reduce, is that the initial value of the accumulator is the first element of the list. Something you need to be aware of that can cause some really tricky bugs to debug if you're using reduce and never getting that first element processed. And then it's a return 55. So we took an entire list and reduced it down to a single value based on a function that was called for each of the elements. We're getting into the fancy stuff now. This gets really powerful. This alone could do the first 2 objectives, the first 3 methods in the homework with like just reduce. And we can still use this underscore shorthand. Even though we have 2 parameters, we can rewrite this using the underscore shorthand if we don't reuse any variables, any of the parameters. So here we have 2 parameters, and the order in which these underscores appear, that's the order of the parameter list, if you want to use the shorthand. At this point, the shorthand might just be getting more confusing, so I won't blame you if you don't use it. That's why I show you the whole thing here. But the order of the underscores will be the order of the parameters. So the very first underscore that's found is going to be the accumulator, and the second underscore that's found is going to be B in this example. So this is my accumulator. This is the element that I'm currently visiting, or B in the previous slide. And Scala will know what to do with that. This is the full definition of the function. All right, any questions to this point? Let's take a little break for some things to digest. Check chat. Just chatting about loops. Yeah.
On the previous slide for some squares,
Mm-hmm. So the type in this example is inferred by Scala. Previous from that?
some squared.
Sum squared is a double.
No,
R-
some squared.
Some squares. Oh, yeah. So the type of this is a function that takes 2 doubles and returns a double. So the type of this variable is a function, and that's the function we're giving to the reduce method. Or is that your question? And then when we moved on to this example, this is still a function that takes 2 doubles and returns a double, but Scala looks at this and infers what all the types are. It'll know, since we're calling reduce from a list of doubles, it'll know that this function should take 2 doubles and return a double. And as long as that, whatever we put there, can fit those types, then it's going to just assume that they're doubles. If it can't fit those types, it's going to give us a type error. and say, yo, you were supposed to give me a function that took 2 doubles and return a double, and you didn't, the compiler is going to yell at you and not run your code. But here we specified it. So here's the assignment operator. Everything on the left is the variable name and the type, and everything on the right is the value that we're going to store in that variable, which is a reference to a function object. To throw a whole bunch of, so much terminology at this point. It's a lot of stuff that you know at this point. And we're talking about Fruit Loops in the chat, so I'm assuming we're good on that. And this is a lot, like there's a lot of small topics here. So if you're comfortable with functions at this point, this lecture is probably not too bad. If you're not comfortable with functions, then it's a lecture that's going to completely lose you. So it's hard to judge. It's definitely a lecture you want to reference, though, while you're doing the homework. Because there's a lot of really handy stuff in here that can cut down the amount of code and the amount of effort you put into the project significantly if you get good at using these things. So let's move on to fold. So we had that problem with reduce where the accumulator variable is just initialized to the first value in the list. That's not always what we want to do. We usually want to process each element. In the previous example, we wanted to sum up the squares. We wanted to process each element by squaring it and then accumulate the squares. So fold is going to solve this problem for us. Instead of just taking the accumulator, it's very similar to reduce, but instead of just taking the first element as the initial value of the accumulator, we're going to explicitly give it in a second parameter list the initial value for the accumulator variable. So here we're going to fold these values. We're going to initialize to 1.0 because we're multiplying. So 1.0, our multiplicative identity, that's not going to interfere with our calculations at all. So we're going to initialize the accumulator to 1.0, and we're going to take the accumulator times whatever element we're looking at. So first the accumulator is 1.0, and we're going to visit the first element and actually process it this time. 1.0 times 1.0 gives us 1.0. 1.0 times 2.0, 2.0. 2.0 times 3.0, 6. 6 times 4, 24. 24 times 5, 120. So now we get every single element processed. I mean, again, we would have got away with it with using reduce for this example because the first value is just 1 anyway, and actually we would have got away with it because there's no processing. But this is going to let us set an initial value for that accumulator variable. So you can read this like from the accumulator pattern. Initialize your accumulator variable here, and then for each element, take the accumulator equals the accumulator times the element that I'm currently visiting. So it's the same as the accumulator pattern from 115 now. This fold gives us the full power of that, where reduce was a little bit limited. Fold is going to give us the full power of that accumulator pattern, but in a functional programming style instead of a procedural programming style, which is everything you did in 115, by the way, was procedural. Now we're talking about, we were talking about OOP, now we're talking about functional programming, 3 different programming paradigms, 3 different ways of writing code. So now we're using a functional style instead of a procedural style. Travis, you're so confused. Why does this give out 120? I didn't do my math wrong, right? Better than 55. So this is multiplying all the values. 2, 6, 24, right? 24 times 5 should be Yeah, Cole's got you. 24 times 5 is 120, yeah. What was the example where we had 55? Because we were summing the squares here, and here we're just multiplying all the values. So the sum of the squares is 55, but I switched up the example a little bit and just multiplied all the values for this example. Maybe all these examples should just sum squares. Would that be more clear? I feel like that it'd be boring seeing the same exact example every slide, though. So we can actually use fold and reduce to change the type of the data as well. Oh, wait. Not reduce. That's my next point, right? Yeah. So we can use fold to change the type of the data. We can't use reduce to change the type of the data because the accumulator is initialized as the first element of the list. It has to remain the same type. But with fold, we can actually change the type of the data. So if we want to start with one input and then reduce one type and then reduce to another type, we can do that. We do have to specify either fold left or fold right for what it's worth. Fold will always call fold left. The fold method only calls fold left. That's all it does. It's just shorthand for fold left. Fold left and fold right are doing the same thing, except either starting with the left side of the list or the right side of the list. Oops, I did that backwards. I did my left and right. I got to do your left and right. So we're going to start at different ends of the list. If you want to change the type, if you want to return a list of a different type than the input list, you have to use either fold left or fold right. So if you want to use just regular fold, you have to specify fold left because fold is not going to let you take two type parameters, give it two type parameters. But if you do fold left or fold right, initialize the accumulator to one type. Whatever type you specify here, that's going to be the type of the return list. And then it's going to be expecting a function where the accumulator is the type that you're returning, int in this case, and the value you're iterating over is going to be the type of the input list, string in this case. So you can use this fold left, fold right, reduce right. You can use these with reduce as well. Reduce, you can't change the type, but you can still reduce from the left or the right if you want to reduce from different ends. The one caveat to this is if you're reducing or folding right, the order of the parameters is reversed. The accumulator is the second argument that you have to give, or the second parameter, and the first one is the element that you're iterating over. So just a little nuanced thing. I don't know why I get why visually you can see this is the accumulator, which is like accumulating values and moving to the left here, and it's moving to the right here across the list. I get that visually, but it is a little frustrating. It's one more thing we have to remember. I kind of wish it was just the accumulator is always the first argument. Would have been easier, I think. But this is the way it is. If you want to use fold right for whatever reason, I mean, honestly, you can just get away with fold, reduce, fold left, reduce left, for this course at least, and not have to think about it. But if you do want to use the right versions, the fold right, reduce right, arguments are reversed. Okay. So let's talk about a few more methods that we can use with lists. These methods won't use any functions. They won't take functions as inputs, but they're still useful for your assignment, so I want to talk about them nonetheless. And they should be a little easier to grasp than the ones we just looked at. We'll cool down for this. We'll cool down a little at the end of this lecture. Sum up the elements of the list. If the list is a type that can be summed up, so if it's int or double or long or float, if it's some numeric value, hit it with a dot sum. It's going to return the sum of all the values. Could really simplify your average method for LT1. Sum, divide by the length. It'll get you there. So sum, it's built in the function. All sum does, all this is a shorthand for calling fold. But it's useful. It can be useful if you don't want to look up the syntax for fold. If you just want to sum these things up real quick, you got some list of doubles, you want to sum them up, just hit it with a dot sum. Done. Easy enough. Just like when we said dot sorted, we didn't care about how sorting worked at that point. We didn't care about comparators or anything. We just said dot sorted, give me your default action, and get it done. Distinct is going to remove all duplicates from a list. This gets very handy, especially LT6. Yeah, LT6. When you have to detect duplicates in a playlist, duplicate songs in a playlist, hit it with distinct, and check, did the size change? Give me my playlist, give me the length, give me the playlist dot distinct, so remove all the duplicates, and check the length. If those two links are not equal, I know I had a duplicate song in that playlist, I'm going down my duplicate song route. So distinct removes all duplicates and gives you each distinct element. So the distinct elements are 1, 2, 3, 4, 5. Get rid of all those duplicates. And slice might be really handy for top K and LT1. Slice gives you a subsequence of a list. So I have this list of elements, index 0, 1, 2, 3, 4, 5, 6, and I'm using the word index here. Lists don't actually have indices, but I'm going to pretend that they do just so this slide isn't a whole essay. So slice is going to take an index to start, which is inclusive, and an index to stop, which is exclusive, and give you the sublist between those indices. So here we're starting at indice 1 for the sublist, and then going up until index 4 exclusive. So 1, 2, 3, 4, exclude that one, and stop at the element right before it. So we get this subsequence of the list. So like if you wanted your top K, slice 0 to K, it'll be exclusive of K. You're going to get indices 0 to K minus 1, which will be exactly the top K elements. Not to give it away entirely for you, but if you're still paying attention at this point, I want to give you something. Reverse, which I realized I had a typo in it. There was a typo in a slide earlier too I didn't point out, but returns of the elements of the list in reverse order. What kind of sentence is that? Anyway, returns a copy. This is supposed to say a copy of, I don't know what I was even trying to say, but it returns a copy of the list, but with all the elements in reverse order. So if I have this list, dot reverse, reverses it. I don't have much to say about that one. Which brings us back to the lecture task, which means I'll see you Friday. Have a good day.